We're going to do the black one down there. So if we go through and look, we're looking at oxygen, carbon, 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 right? Oxygen has the highest atomic mass, so that immediately gives us the 1. Now deciding between our other carbons. The blue one goes out to 2 hydrogens, and then a carbon. The purple one goes out to 2 hydrogens, and then a hydrogen. The orange one goes out to 2 hydrogens and then carbon, which then means the purple one's the lowest priority because of the hydrogen versus the carbons, so it gets our 4. If we move to the next one in our chain, our carbon goes out to 3 hydrogens. Our carbon goes out to 1 hydrogen, 1 oxygen, and another oxygen, where that one is a phantom or ghost. I think I've called it phantom, right? I haven't called it a ghost one. Okay. Either way, it didn't really matter because we're now going out to oxygen versus hydrogen, which means 2 and 3. Make sense? Yes?
I thought the phantoms were only with carbons.
Technically that is with carbon. We're starting at this carbon, and it's now referencing sorry, this didn't really make much sense because pointing to it on my screen. We're referencing this carbon of our carbonyl. Our phantom applies to any pi bond. Okay? So it immediately goes out to 1 oxygen as a sigma bond, and then it has another pi bond out to an oxygen. Okay? If there had been an oxygen out on the blue one, we would have then gone out to our oxygen to see what's connected to it, and it would have been connected to a phantom carbon. Okay, so our phantoms are whatever atom is connected out there.
So the fact that the carbonyl group doesn't matter in terms of assigning priorities?
That carbonyl group doesn't matter at all as far as assigning priorities. Typically what students will go through and do as a mistake is say that the orange one is priority number 1 because that is a bigger group than, say, our oxygen. It's atomic mass, not molecular mass or mass of the substituent. So we're literally going out atom by atom until we find that difference. Okay, so we have to watch out for that. That is very commonly tested on. If we now evaluate or connect, this one becomes challenging because to assign this, where does our lowest priority have to be aimed? Away from us. And right now our lowest priority is aimed in the plane. Okay, so that's not aimed away from us. So I will fully, I don't know a good word to describe it, so I'm just not going to say it. I'm just going to say I will fully. And what I would do is redraw this. But in this redrawing, what I'm trying to do is a rotation. That lowest priority must be aimed dashed or away from us. So there's my 4th carbon. As I do that rotation, what's going to happen to that red OH? It's going to rotate into the plane. That blue position will be wedged. And what was the other color? Orange. Didn't rotate. So what we're doing is rotating about that bond to get that alignment. Blue I said was 3, red I said was 1, orange I said was 2. 1, 2, 3, that goes clockwise, which makes it R. Clockwise is R. Okay? Very easy to screw these up. Be careful as you go through and manipulate them. Okay? On a test, that is exactly what I would go through and do, except I wouldn't have done colors. I would have done the number of atoms, not the number, but the priorities. Okay? And I would have redrawn that. Okay? Yes, that takes time, but that guarantees I get it right. Okay? If I don't do that, I don't get it right. Okay? Or I get it wrong more than I care to admit. Okay? Are there ways that you could look at this to make that proper assignment? Yes, but it comes down to what are your odds of success? Okay? I would argue if your odds of success on assigning this without doing that secondary drawing are less than probably 80%, you should be redrawing it. Okay? If you can do it at greater precision than 80%, then fine. Just look at it and make your assignment. Okay? Kind of makes sense? Okay. I will reference that some people will build a tetrahedral carbon out of their hand and try and align it. Right? That could be, your hand doesn't always work perfectly for it, but you could try and build it with your hand, which is now going to be locked up in that position. Right? And then you can try and do the rotation to look at it from the proper angle. Okay? So I have heard people referencing that when they go through sections like this in the test, it looks like they're casting magic spells in the back of the classroom because that's what they're trying to do. Right? That's fine. I don't have any problems with that. You're allowed a model kit, so freaking use the model kit. Right? And then you don't have to worry about doing, something to devil. Okay? Makes sense? At least not more than once during an exam. Or like raising your hand, right? Let's just continue on. Let's let that one die. Okay, thank you. So Fischer projections. I want to address this as quickly as I can. If we look at this molecule, we've got a lot of chiral atoms in it. Chirality, wedges, and dashes, three-dimensional spaces, confuses the hell out of biologists. And to be fair, everybody else. Okay? So what we end up doing is changing our perspective on the molecule to simplify how we look at it. Okay? This sounds a little bit weird because the process of this simplification isn't necessarily simple. Okay? This is aligning it towards Fischer projections. We orient the carbon chain, so our vertical axis needs to be vertical. Just roll with it. Okay? So there's our carbon chain on that vertical axis as opposed to horizontal. Okay? The next part that becomes tricky is every carbon in that backbone needs to be aimed away from you. If we oriented that on the backbone, if we oriented it that way, where are the carbons? They're left, right in the plane. They have to be aimed away from you. So what do you have to do? You're going to have to take the molecule and turn it. Okay? So as we turn it, we would end up with something like this, which I know looks exceedingly confusing, but let's start from our carbonyl. Okay? Our carbon chain is going away from this center carbon, away from it, but now we're in the back plane, because it's a zigzag, the carbon chain is going to be coming at you, away from you, at you. Kind of see it? Right? So that's not oriented according to Fischer projection. So Fischer projection says, continue to do rotations until the carbon chain is always aimed away from you. So that first one was fine. So we do the next one, look what happens with the OH. We would have to rotate that so that that carbon would be aimed away, or that bond would be aimed away. Kind of, sort of? We'd go through and do that for the entire backbone of the structure. And what we'd now be in is what is known as a Fischer projection. Okay? Some of the extra rules. Number one, our highest priority carbon has to be at the top of our carbon chain. If we take a look, we had a carbonyl carbon versus an SP3 carbon. There's a sneeze in there somewhere. Okay? Technically 2 oxygens connected to it as opposed to 1, so the carbonyl is at the top. Okay? When this is all aligned, then the substituents, things connected to the carbon backbone, will always aim towards you, okay, wedged at you, either left or right. Because that is the case now, all of that backbone can ultimately be simplified out. Okay? So what it becomes, because it looks like I didn't actually draw it or show it, and we can simplify our drawing to look like this. Do we see any wedges or dashes? No, so it looks prettier and cleaner. Okay? The other advantage to this is when assigning R and S, look at your substituents and decide whichever one's highest priority. Okay? In this case, the OH is on the right-hand side of the structure, which makes it R. That's supposed to be an OH. Here, the OH is on the left-hand side of the structure, which makes it S. Okay? And it can simplify that assignment process. Okay? And I might have actually goofed that because I don't memorize that. Yes?
Can we ignore the middle parts? Meaning, like, can we just jump from the first structure to the last structure? Eventually that.
Yes. So in the representation, all I'm trying to show is stepwise how we progressed from what we would see in OChem to what we would see in a different class. So this is OChem to what we would see in biochem, okay, or a biology class. So why were we allowed to do that transition? A lot of it just comes from this is why Fischer wanted to view the molecule this way. Okay? Why else would he want to organize this? If we now take a look at that molecule and look at it, what it actually looks like in 3 dimensions, as opposed to now our shorthand version of this, it looks like this. Okay? Where our viewpoint is constantly oscillating around that structure. So our carbon chain cyclizes, okay, or circles into a spiral. Why does that become super important when we're talking about this molecule? What is this molecule? Isn't it glucose? Yes, it is glucose. What is special about our carbohydrates? They cyclize. They turn into cyclic structures. Why do they turn into cyclic structures? In this Fischer projection, that oxygen gets really close to that carbonyl, and it can make a connection there. If it makes that connection, how many atoms do we have in a ring? Why would it want to form a 6-membered ring? 6-membered rings are more stable. That's our cyclohexane. And we end up with chairs. And it turns out that that attack produces 2 chairs. Okay, 2 different conformations of glucose. One is higher in energy than the other. How did biologists find this out? They found the really high energy one and were like, oh, it's glucose. This is how glucose is. Right? It's this high energy form. We go, oh yeah, yada, yada, yada. And then they were like, oh crap, there's this other form of glucose. Well, we found one, so we'll call it alpha, and we'll call the other one beta. Why? There were 2 different attacks. Right? Those 2 different attacks came from organic chemistry. If you studied organic chemistry, you could recognize that there were going to be 2 possible products. One is going to be higher in energy than the other. The higher energy one is used in fat storage, okay, or energy storage. Guess where the other one's used? Cell structure. Okay? And all it is which way did that oxygen attack? Did it attack this from the top, or did it attack it from the bottom? Why is it attacking from top or bottom? What is it reacting with? What about the carbon? The pi bond, which is located above and below the plane of that atom. There's 2 potential places the oxygen can slide in and do that attack. If we understand molecular orbital theory, we have that understanding in our belt, and we can see that result. If we don't, what do? We memorize. Welcome to biology. Okay? So, this defines it. See, I knew I screwed it up. This defines it for our Fischer projection, so it simplifies out our drawing, and we can end up with that. For our RNS determinations, you can assign as normal, but we just change it to the opposite. Okay? Or actually, no, here we go. A highest priority in the bow is on the right, R. So we look at our bow tie. Oxygen's our highest priority, R. Oxygen's our highest priority, so S. So this is R, S, R, R, NAR, none of the above. Because that is not a chiral atom, and is not a chiral atom for a couple reasons. Why not? 2 hydrogens, and
It's connected to the.
is it in the Fischer? It's not drawn into the Fischer projection because it's not a chiral atom. Okay? So, that can simplify our understanding, and that's why Fischer kind of invented that viewpoint, because it works. It allows us to assign those RNSs pretty quickly. Okay? I do want to note that there's a new label system that shows up in biochem. You'll hear reference to capital D and capital L. Okay? What do those reference? This last carbon, the penultimate carbon, the last chiral carbon, if your highest priority is on the right-hand side, that becomes D. You're like, that's stupid. How would you figure it? Well, L left begins with L, so really, right? What is the D standing for? Dumb. Did someone really say dumb? Dextro, okay, for right-handed. Okay, so when you think about people have a high dexterity, sorry, lefties. Okay, it's in reference to someone being good with their right hand. Okay, so dextro because it's on the right-hand side. How about this one up here? D or L? Okay, and for those people at home, I'm talking about this one, D or L? Is that the second to last carbon? No. So it's not D or L. Has nothing to do with D and L. D and L is literally that last carbon. Where's the highest priority? Is it on the right or the left-hand side? If it's on the right, it's D. If it's on the left, it's L. So what about that assignment up there where that OH is located? Okay, we could reference it as R and S. Okay? Entirely different nomenclature system. Okay? Again, meaning right and left. But capital D and capital L are not the same thing as R and S. Capital D and capital L, literally that last position. R and S could be applied to everything. Okay? So how would we know that blue one? Let's see, did I actually sequence it right? Yeah, I did. How do we know that blue one? We look at maps and no thank you, I don't want to learn that. This is biochem. I agree, no thank you, I don't want to look at this. Okay? And what biochemists go through and do is say for that particular pattern, that is known as erythro. That one is known as ribo. That one is known as gluco. That one's galacto. And how do we know we have D-galacto? Because that second to last one has the OH on the right or the left. That differentiates it. We would have to know that galacto, which I think is one of those, okay, has that other patterning of where all those OHs are located. Okay? So when you think about carbohydrates, that's ultimately biochem's nomenclature system. They just go, well, D and L for looking at that last position, and then everything else you just memorize. Because why? Because I didn't want to come up with a better nomenclature system. I really hope there's a better logic to it than that. I haven't been exposed to it, but I hope there's a better logic system than that. Okay? So let's take a step back away from that and now look at kind of the lab side of this. So we've got enantiomers, diastereomers, and we can classify all these things theoretically now. Okay? One of the big issues we now need to realize is that, yes, we know there's a difference when we look at the drawing, but I don't look at a drawing. I have to look at an unknown sample and decide which one it is. One way of figuring out would be eating it and being like, well, damn, I died. That's a bad method. Okay? So I want to have some kind of method to study it, to figure out what's going on with it, which means I have to know something about the physical properties of these materials. Okay? When we're looking at diastereomers, what do you think is going to happen with their physical properties? Should they be different or the same? Okay? So these are both two representations of the same thing. Okay? We have one that kind of looks like this, stacking out, ring, or ring stacking out like that. Are those going to interact with each other differently? If they interact with each other differently, that means different surface contacts, which means different physical properties, like boiling points, melting points. Those properties will be drastically different. So I would be able to distinguish two samples that are diastereomers of each other by looking at their melting points or boiling points. Okay? I would be able to tell they were different because their melting points and boiling points would literally be different. Okay? So our diastereomers are pretty straightforward to deal with. Okay? Because their physical properties are different, everything about them can also be different. Melting points different, boiling points. I can separate them differently from each other. Okay? Envision trying to grab one of these. Okay? The one with both the pointy things aimed up, you could probably grab just to the side of them and not worry about it. But with one's up and one's down, you got to be a little bit more careful, right? Okay? So it changes that interaction. Okay? What becomes the problem with enantiomers? they have the exact same relationship, okay, just mirrored. Which means if I look at how my right hands stack, they're all going to stack beautifully. And if I stacked a bunch of left hands, bit morbid, but we chopped off everybody's left hand and stacked them, okay, they would interact the exact same way as a stack of right hands, but just left versus right-handed. Which means their melting points and their boiling points and their physical properties will all be exactly the same. So if I have an R, an enantiomer, and an S, I can't differentiate those two solutions based off a melting point, because it'll have the same melting point. Right? So I need to come up with some way to separate them. Okay? And that is what makes this difficult. Okay? So we've got some examples up here. We already talked about the thalidomide. Naproxen has two versions. One is your anti-inflammatory. The other one's a liver toxin. Okay? The one I tried to play with, okay, with some honors project was taking limonene. We can isolate limonene from citrus. Okay, that smell that you're used to smelling with oranges is usually due to limonene. We'll do a lab on that next week. Okay? What we could do is take that same compound and change the chiral atom to just the other direction, and it now smells like turpentine. Like, oh, lovely oranges. Oh, turpentine. They smell really different. Why are they smelling so different? What are they interacting with? Or, right? Oh, here just popped. They're interacting with your nose, and your nose is part of your body, and you are chiral. So that same molecule, by just changing the orientation in space, will change how your nose interacts with it, and it now signals a different thing to your brain, right? Which is kind of neat. So if I'm running through an experiment, I want to be able to come up with some way to separate these away from each other. But if they have the same melting points and boiling points, that becomes tricky. So how do we do it? Number one, don't. Okay? The easiest way to avoid that separation is to never make that separation a possibility. So when you run your experiment, ensure that you don't make both enantiomers. That's the first and primary priority. Okay? Sometimes you'll be forced into it, so how can you do it? Okay? You can separate them on a chiral medium. Okay? Imagine this wasn't going to cut up your hand a whole bunch, but if we had just a bucket full of left-handed and right-handed scissors, how could we sort out the left and right-handed scissors? You're like, I have no idea. Stick your hand in them. If it fits in your hand, that was a right-handed scissor. Okay? If it doesn't fit in your hand, then left-handed scissor. Okay? Your hands are chiral. So we can separate enantiomers away from each other if we can introduce a chiral substance to separate them for us. Okay? That becomes expensive very fast, okay? But it can be done. Okay? The next one is similar to 2, except it's a little bit more reactionary. We're going to react both with a chirally pure compound, and then I can separate normally. Well, why? So here's my enantiomers, right? Here's my pure compound. What is the relationship between those products? Anybody want to say they're enantiomers? Yeah. These two are enantiomers. Do I have the thing in the red box anymore? Or the purple circle now? No, what do I have? I have this thing. And I have this thing. Are they still enantiomers? If we look here, yes, the chirality changes. It mirrors, so fantastic. That would be enantiomeric. What happened at the next chiral atom? Stayed the same. And the next one? Stayed the same. Which means we did not mirror these. These are not mirror images of each other. What are they? Diastereomers. Because they are now diastereomers, what can we do? We can physically separate them. Okay? This one's a little bit more challenging than 2, because in 2 it was just I put my hand into the scissor box and figure it out. Okay? In 3 is I'm going to throw a chemical in at the scissors to change the composition of the scissors that will then allow me to physically separate them. That requires a chemical reaction. Every time you do a chemical reaction, there is a loss. Okay? Think about it like relationships. The more relationships you have, the more torment it takes on you. Okay? So you find one and just hope it's the best and be happy with it. You just got to weigh counterbalances, right? I'm not a relationship advice columnist, for the record. Don't trust everything I say. So these are now diastereomers. That diastereomeric relationship now allows us to separate those, okay? Because we've now made them into diastereomers. Okay? Last way, which is supposed to say 4, we say, F it, I can't do it, but I'm at least going to tell everybody that I'm going to kill them with whatever drug I'm getting them. Okay? What that is our enantiomeric excess. Okay? And in an enantiomeric excess, okay, it is just the percent of whichever one is higher, because it may be different. Right? I may decide that I wanted the R version of it, not the S. Or I may decide I want the S and not the R. So the enantiomeric excess just says one of them is higher, and whichever one is higher, I subtract the lowest from it, percent-wise. Okay? So all we're doing is reporting that we screwed up. Okay? If we perfectly screwed up, and we had equal amounts of both, what's our enantiomeric excess? Perfectly screwed up. It would be 50-50. It would be 0. Okay? That would be an awful reaction. An awesome reaction where I got only 1, the enantiomeric excess would be 100%. Okay? So we're looking at that scale and deciding those relationships all the way through it. Okay? This does assume that I have some way of figuring out what those percentages are. Okay? That requires another form of spectroscopy. Okay? Can I verify this before I ingest it? Yes. Light interacts with chiral molecules differently, okay, which is kind of neat. So we take our light, we clean it up, that's the point of the filter, or the monochromatic filter, and then we pass it through a polarized filter. So light has waves, so it goes all different directions, right? If we pass it through this polarizing filter, it'll change the direction of the light to only align with one direction. Okay, for those of you like, wow, we can do that, put on your sunglasses. They're nice sunglasses. Guess what they're doing? Exactly that. Okay, they're polarizing it. Which then actually asks another question. If I polarize it so it's all aimed one direction, could I cancel out that light altogether? What if I took another pair of sunglasses that were polarized and aligned it with it? They'd both be polarizing the same way, so it wouldn't cancel. What if I just turn it by 90 degrees? Now it's going to cancel out that other vector of light. Take 2 pairs of polarized sunglasses, you'll see light does not pass through, okay, when aligned 90 degrees. Nifty. Okay? You don't have to believe me, you can test it. It's true. I've done it multiple times. Okay? Particularly right before paying for sunglasses. Are these really polarized? Okay, yeah. Okay, now we've set it at our sample. Okay? That polarized light is aimed one direction. Okay? If there's no chiral atom, the light doesn't change. It just passes straight through. Okay? And it aligns directly on that axis. But if there's a chiral molecule, the light will interact with it. Okay? And it will cause it to rotate. So R will cause it to rotate one direction. If I have the enantiomer S, it'll cause the light to rotate the other direction. Okay? Note in this statement, I'm not saying R rotates right and S rotates left, because it doesn't. Okay? Those of you being like, oh, R rotates left then. No, it doesn't. Okay? It just rotates. Okay? And we know that enantiomers rotate opposite directions. Right? And for those people going, well, why is that so different? Every molecule interacts different. Okay? We're looking at one where we are studying the structure versus the structure or science studying the sample. There are 2 different systems behind that. That's why we don't get a perfect alignment of those names. Okay, so be careful associating those. So if we go through and look at how that light rotates, because I can't call R and S, I have to invent a new naming system. And we call it levorotatory and dextrorotatory. Not to be confused with capital L and capital D, because those mean different things. This would be lowercase l and lowercase d, or negative and positive. For those being like, what the? I agree. This is not the cleanest section of material, okay? But that's how it associates, right? So the big thing that comes out of this is not the same as R and S. This is not the same as capital D and capital L, okay? But these things here are the same as minus and plus, or you can call them lowercase l and lowercase d. Why do we have to call them lowercase l and lowercase d? Because capital D and capital L was used in a different system. Why? Because science hates you. Okay? So ultimately what we want out of this is to recognize, okay, a couple big things. Well, really just one big thing. A chiral molecule rotates light one direction. Its enantiomer rotates light the other direction. So let's say an R enantiomer rotated the light minus 5 degrees. What is the S? Plus 5. Equal and opposite. Okay? And that's a really big thing to know. Equal and opposite. Can we make this more difficult? Yeah. Okay? And I'm kind of with you on the let's not, so we'll do this kind of fast. Okay? And there's a bunch of equations. Breathe. That light has to interact with the sample. What happens if you change the concentration of the sample? Changes the interaction with the light. Okay, which means when I'm looking at my output, I have to account for the concentration of the sample. Does that make sense? Every time light hits a chiral molecule, it rotates a certain amount. If there's a whole bunch of molecules in my sample, it's going to rotate a lot. Okay, so I have to be aware of that so that when I report my rotation out to the outside world, they know the concentration of my sample. So that has to be factored into what I report out. Okay? You all did the recrystallization experiment, or those of you that did the recrystallization experiment. Okay, you ended with about 0.05 grams, right? Some people. Out of 100 milligrams, 0.1. Okay? So 0.05. I ended with 0.5. Who did the experiment better? I did. I started with 0.1 grams, and I ended with 0.5. Did I purify that?
No.
No. Okay? That's why we have to look at percent recoveries, not absolute values. Does that make sense? So you had a 50% recovery. I had a 5,000, I can't do math, 500% recovery. You can't do that. Okay? That doesn't work. Okay? So we have to report a normalized system. That normalized system is this alpha in brackets. It's going to be the rotation we observed, and it's going to be divided by the concentration. It's also going to be divided by this L. Where have you seen L before? In Beer's law, okay, where we're looking at concentration and path length and all of that. The longer the path length, the more opportunity I give the light to impact a molecule, which means I can get more rotation with a longer path length. Okay? So the same principles that go into Beer's law are also going into this. Okay? So concentration, I don't know why they did it this way, but they did. Grams of compound per milliliter of not of solvent, of solution, of the whole solution. Okay, L is your path length of sample in decimeters. Why decimeters? Because nobody was using it and they felt bad for decimeters. Okay? Those things have to be factored in to get your proper rotation. Okay? Where does this come in handy? This comes in handy back to that reporting out what was my enantiomeric excess. Okay? Your enantiomeric excess is the rotation of whatever you're testing divided by if it was pure. So if you had a perfect system, your enantiomeric excess should be 100%, which means the rotation of the mixture should be the same as if it was pure. Okay? This can allow you to do a whole bunch of calculations if you so wanted. You probably don't want to, so don't stress. Let's think about how we could ask questions about this. Which of the following show optical activity? An R enantiomer. Is that going to interact with light in only one direction? Yes. Why? There's only one enantiomer. Okay? So yes, that one is optically active. How about a meso compound? What does meso mean? There's an internal mirror image, right? Okay? So if one was R, the other one is S. So light comes in, it sees the R, it rotates one direction. What does the S do? Exact opposite. The net result is zero optical activity. How about a mixture of enantiomers? Should that have optical activity? Yes? Why?
The ratio.
It has to do with the ratio that comes out of it. Okay, that's an unequal ratio. Okay, so it'll see the S and then it'll get canceled out by one subset of the R's, but then I have an excess of R's, which means it's going to rotate. Let's compare that up to this one. Which one should rotate more?
The R.
Why should the R enantiomer, the pure R enantiomer, rotate more?
It has no S.
There's no S to cancel it out. Okay, how about a mixture of enantiomers, 1-to-1, R to S? No optical activity. It sees one, it cancels. Okay. How about a mixture that has a 0% enantiomeric excess? What did a 0% enantiomeric excess mean?
You have the same.
I had the same amount of each one, which means no. Kind of, sort of? Sure. That's good. I like the confidence. This system here of a 1-to-1 becomes so special and actually relevant for a lot of the, or one of the reactions we do after spring break, that it gets its own name. It's an equal ratio of those, right? And if we look up equal in some language, I actually have no idea. It's called a racemic. It's a racemic mixture, which is the adjective of the mixture. I could also reference it as a racemate. It would be like, that's stupid. Why would you do that? English language. What has now happened? Racemate is now a noun. So depending on which article of speech I want to use, I will change the ending of it. If you see that race part, you're looking at a 1-to-1 mixture. Okay? Kind of, sort of? You're like, this sucks. I agree. Okay. I don't want to ask this question. Okay? I would recommend that you take a swing at it, take a look at it, and think about it, because this type of question can and will show up. Okay? What you can do is reason through it to the best of your abilities. Specific rotation of S-iodobutane is positive 15.9. Okay? Determine the percent composition of the enantiomeric mixture if the specific rotation of the mixture is negative 3.18. Oh my God, there's too many numbers and calculations. Take a deep freaking breath. What can you tell me about the mixture right away?
That's S favored.
Okay, I like where you're going with that. You're saying it's S favored. Why is it S favored?
15 compared to negative 3.
15 compared to negative 3. A positive rotation was S. What does that mean the negative rotation is? R. So right away, what do you know? It's not S favored, it's R favored.
Wait, why?
Okay, look at the rotation. If it was S favored, what should its rotation be? it should be positive. The rotation of the mixture is
Oh, the final.
negative. It's rotating the other direction, which means it's R favored. Okay? I could bet you'd see a 50-50 percentage up there. What do you know right now? That answer is wrong. I would bet there's an answer that says 75% S. What do you know? That is wrong. Okay? Could probably even bet 75% R, 25% R. I'm literally making up numbers, by the way.
75.
You think it's 75%? Okay, if it was 75% R, the vast majority of it would be what? The R enantiomer, which means our rotation should be R favored. Is this R favored? How much is it R favored? A lot or a little? A little. Is 75% a lot or a little? A lot, which means it's probably 25%. We didn't have to do a single frickin' calculation. You see that? Okay, and for those being like, dang, that's just hard, then you do all the freaking math. That's cool too. Okay? The math to do all of that, whoops, let's erase those answers. Okay, so first and foremost, you should absolutely be able to nail down that R favored. Okay? That will eliminate at least one answer, if not two. Does that make sense? Yes.
So if we know it's R favored, and it's 25%, so then what's 75% of the rest of it? Or, you know what I'm saying? Like,
Yeah, I didn't do the math very well, did I?
I was gonna say, isn't 25% R the same thing as 75% S?
Let's try that. Math, man. Shh. Okay. Some number where it's larger than R. So it's not a vast excess of R. Okay, which might have been where you were going with the 75% S or R, and I just did the math horribly wrong. Okay? But you guys did it properly too. That would also then mean 25% R
75%.
would have to be wrong. Okay? Does that make sense? So you can get a scale of those numbers to come up with those approximations without actually having to crunch numbers. Does that make sense-ish? Okay. For those of you who want help, I will walk through that again if you would like after class. Okay, I don't want to do it again. I will point out on how to go through and solve this. Okay, you're looking at that enantiomeric excess. You're looking at these two equations and setting those up. Number one, you'll get an enantiomeric excess by comparing these two values. You do have to be a little bit careful with those, mixture versus pure, to ensure you're looking at the right one. Okay? You then also have this percent of highest versus lowest. The last equation that you need to acknowledge, which nearly everyone forgets, is what is the percent R plus the percent S? 100%. That equation, most people just ignore. You need that equation to actually solve. Okay? And you can actually go through and do that full solve all the way through. Okay? And I literally don't know what the numbers are, clearly. Right? Okay. Which gets us to the fun section. Structure and how to prove. We've got 4 forms of spectroscopy. Ultraviolet, infrared, mass spec, and NMR. In the next half an hour, I hope to cover everything about mass spec that I want you to get. Ideally, we even get into NMR a little bit. We'll then cover NMR all day Wednesday. Next Monday is IR and UV, which are ultimately quick, fast memorization things. Okay, so there's very little application. Mass spec and NMR require a sizable amount of application, so I want you to have the weekend to study them. Okay? Why study them? Guess what next Wednesday is? The exam. Okay? To give you an idea on where you should be, okay, the lab was assigned a spectra packet that had a whole bunch of these. And on last Wednesday, I said you guys should all be working on it, whether you're in the lab or not. Okay? One of those will be on your test. There are 12, I think, in there. Okay? You can probably eliminate 4 of them because they're stupidly hard. Okay? So I won't ask those on the test. Okay? But then that leaves the other 8 that you need to be able to solve relatively quickly on the exam. Okay? For those people in the lab, you were assigned to do 5 of those due next week, Friday. Everybody by this Friday should have 4 completed. Okay? Why 4? You want some freaking time to study for the exam. Okay? If you go through that packet and you solve those 4, you've got a lot of the fundamentals down. Now it's small, nuanced questions. Okay? Make sense? Yes?
If you're not in the lab, where is the packet?
It's on Canvas under files is about all I can give you right now. I think I sent an announcement about it. And I can dig it out and repost. Okay, which gets us to this. What are we looking at? IR. Okay, yes, you should be able to identify it's IR. That could answer a question. What else do you see? CHSP3. Do you see anything else? You're saying you have a CHSP2? Presumably that's what you're pointing at?
I think Alteal.
Okay, this is not CHSP2. That big tall one is ROH. I would accept that small shoulder to be a CHSP2. That's a bit dicey to assign. Carbonyl 16, 17, calling that a carbonyl, possible. It's a bit low for a carbonyl, right? Okay. Carbon double bond carbon is more likely. That doesn't mean it's not a carbonyl. Okay. The next one next to it. Okay. All 3 of those taken together is probably an aromatic, C double bond C coming from an aromatic. Okay. We just spent 1 minute and 15 seconds. You should be half that to get that same information.
Can the first one be an NH?
No, too intense. A lot of that patterning comes from familiarity with looking at spectra. This is why that spectra packet is there. This is why you have a textbook that shows tons of spectra. You have to have that familiarity with this. This isn't just you know that something shows up in that range and it's good. It has to match certain patterns. You have to have seen those patterns. What are we looking at? Mass spec. What else do you see? Okay. See a big tall peak there. We have to pull out our magnifying glass to look down there. 1, 2, 3. I see 93.
Nitrogen.
Odd, so it's nitrogen. Okay. 93 minus 14 is 79 of that remaining mass. It's carbon and hydrogen, 12 into 79. Which is 72. I just remembered that. 8. So I've got C6H8N as a possible formula. I got a little bit more time. What could I do? C5H20. And at this point, I'm really pushing my time. 12 and 7. Okay. Is that a possible formula? Nope. Why not? Or 2n plus 2, where n is 5. The max I could have had would have been 12. So there's a possible formula. That was about a minute. I didn't do as good a job counting that one. What are you looking at now? Carbon NMR. What do we see?
1, 2, 3, 4, 5, 6 unique hydrogens.
6 unique carbons.
One's an alkane.
Alkane.
The rest should be aromatic. Yeah.
That one as a carbonyl makes me a little bit nervous, but I usually don't use the carbon NMR all that much. It's starting to get a little bit low for 160. I would push the carbonyl up at the 180 to 200 range.
So how do you determine that's alkene and that's the carbon?
How do we know those ranges? You have to memorize particular ranges. So there's a cheat sheet that is offered in the tutoring center that has IR, our chemical shifts for our carbon NMR, our H NMR, and it doesn't have mass spec on it, but it gives you some information about NMR. Okay, that sheet memorized. Okay, you have to have that nailed down. The next part, the back of it, is an organizational chart. Okay, ice tables. Do you need ice tables to solve equilibrium?
No.
Everybody's like, yeah, of course you do. No, you don't. Not at all. You don't need ice tables at all. Why do we use ice tables? It's only an organizational structure that allows you to consistently solve correctly. That's what this is. It's an organizational structure that allows you to consistently solve correctly. Once you become advanced enough, do you need ice tables? No. Once you become advanced enough, do you need an organizational structure for NMR or spectroscopy? No. None of you are advanced enough. Use the sheet. Well, somebody might be. I don't know.
So is that not another 2%?
So for counting it out, nuancing, being like, well, how many are there? You're spending too much time. Okay, that's how fast this needs to be. Real quick. Okay, then go backwards and be like, well, none of my answer choices had only 6 unique carbons. Now you can ask yourself, maybe there is one potentially hiding in there. Now what are you looking at? H NMR. What do we see in the H NMR?
4 unique hydrogens.
Okay, we see 4 unique signals. Now what?
Take our question. You gotta look at picture papers.
Okay, I didn't give you the integrations here because I built the slide a bit too fast. We could cheat and look at relative heights of these. Okay, I would bet this one's going to be a 1, 2, 2, and a 3 or a 6. Okay, why able to do all that so fast?
Experience.
Based on
Some of it is experience. Look at all of these are roughly the same height, right? Okay, but this one's only made up of 1 peak. So if I'm thinking about height, I should be stacking each of those peaks on top of each other. So this first one is this, plus that middle one, plus that next one. This, plus the next one, plus the next one, plus the next one, plus the next one, plus the next one. These two look roughly the same in intensity, and both look taller than that middle one. Kind of makes sense? That's sort of ballpark taking into consideration the width of those signals. Okay, that is much more challenging. Does the ACS expect you to do that? Yes, I have no idea why. Okay, but they do expect you to make those assessments. Okay, I expect you to be able to use the integration information I give you. Okay, you shouldn't even be evaluating integration information yet because I deleted everything. Fudge. Thank you. I had 4 unique carbons followed by chemical shift. I have 3. Thank you very much. You should talk to the people in the fundamental class. They're still complaining about my chlorines. They're like, why do you keep talking about uranium? Jerks. This 2 to 3, and everybody's like, that looks like uranium. Yeah, shush. The 2 to 3 range is a giant question mark. Okay, that doesn't mean you don't have information there. Okay, but I would argue there's too much stuff that could fall in that range. Only analyze it if you have to. Okay, so there's a questionable assignment in there. Now I could move to integration. In that integration, I did a real quick walkthrough. I said 2, 1, 2, and 3 or 6. Probably 3 if I'm going to be honest. Okay. And that's raw ballpark based off of size. If I have 2, that means I'm looking at this is getting me information about those. I'm attempting to come up with a structural piece as quickly as possible. Okay. After I've done integration, what do I do? Okay. Probably see if I can come up with an answer real quickly. Okay. If I can't, then I would probably skip it at this stage. If I got time, I'll double back and dig into the multiplicity. Multiplicity is the number of peaks per signal. Starting left to right, I've got 3 peaks, which means 2 neighbors, followed by 1 peak, which means 0 neighbors, followed by 1, 2, 3, 4, 5, 6 peaks, which means 5 neighbors, 3 peaks, which means 2 neighbors. I was right about that being a 3. Okay. With that information, I could now start to build on the pieces that I've already built. Okay? That's the point of the spec.org file, is slowly layering that information in. Sometimes you have to dig straight into it, sometimes you don't. Don't dig into the hardest part if you don't have to. Okay? With that, what happens when we do mass spec? Okay? We take our sample, we put it into the instrument, and that instrument fires some kind of ionization system at it. Okay? There are different forms of mass spec, but ultimately all they're trying to do is explode apart the molecule. So you're putting in thousands of your little molecules, probably more than that, and the system now explodes those up into pieces. Okay? At its simplest level, we're putting an electron beam at it, which ejects an electron from the molecule. Because it now is missing an electron, every single one of those pieces is positively charged. Okay? That molecule now has an opportunity, if you will, to start falling apart, depending on which electron was ionized. Okay, what do I mean by that? Where are there electrons in methane?
On the bonds.
Let's make it ethane. In the bonds, if I ionize and remove one of those electrons, what happens? That bond no longer exists. Notice in that case, I have a positively charged piece and a radical. Because the radical is unstable, it just kind of dies at the side of the instrument. Okay, and gets purged out later. The cation can now move across. It moves across, and that's the point of this magnet. Okay? The magnet is polarizing that and allowing that positively charged particle to move. It is moving through a medium that slows down heavier particles, which means if it's a very light particle, it moves very fast. If it's very heavy, it moves very slow, which means by the time it hits the detector, we can correlate time to the mass of the particle. Okay? Where else could I have fired and ejected an electron from my ethane structure? Where else are there electrons?
Hydrogen side.
Okay? We could have tried and ionized one of those bonds. Okay? So it could have ionized to form H+. It could have also ionized to form that. That's 2 possible pieces that could be moving down the pike that I could then detect. Depending on their individual reactivities will depend on if they actually make it all the way out there. Okay? Where else could I remove an electron? How many of you think there are no more electrons? Different hydrogen. Aren't all the hydrogens chemically the same? Yes, so I'm going to say no to the hydrogens. I'm going to say no to the hydrogens, not a different hydrogen.
All the electrons are in a bond.
All the electrons are in a bond. Everybody agree? How many electrons does carbon have? How many electrons does carbon have? 6. There's 2 carbons. Oh God, wow. Someone might see where we're going. Okay. There's 2 carbons, so we're at 12. Plus 6 hydrogens, we're at 18. The electrons are only in bonds. How many electrons are in that drawing? 12. Where the hell did those other 6 go? They left? They don't exist? There are electrons still in the carbon atoms that were not involved in bonding. I can eject an electron from a carbon atom. I can eject an electron from the core of the carbon, making that whole molecule now positively charged. Did I change the mass of my particle? No. In fact, that is the exact mass of the starting substance that went in. There's my parent ion. That's my M plus peak. Okay? That's what happened. I ejected a core electron in that process to make the positively charged thing. It didn't have to be a bond. Okay? The more complex your structure becomes, the more different locations you could eject electrons from the structure. Okay? Each of those cases needs to generate a stable structure. Because if it's not stable, what happens? Each time we eject an electron, we have to make a stable or somewhat stable structure. If it's not stable, what would happen to it? It will interact with the other particles in the process of making it to the detector, which means we may or may not see it, and we may get odd results at the end. Okay? Which is why when we're talking about mass spec, we're talking about all of the most stable pieces. This is a horribly morbid example, but if we blew up a car, okay, we expect the car to explode in different patterns or according to different rules, depending on where the explosive was located. This is why we have forensic experts that can tell you who made the bomb, where they placed the bomb, and how much damage it would have generated had it gone off, or had it gone off, like what were we able to salvage, okay, after the explosion. They're able to do that because we know how things break apart. This is no different. Mass spec is the forensic scientist studying the explosion of a car. Okay? And when we explode a car, we don't expect the entire hubcap to shatter. We might expect the hubcap to be found hundreds of feet away, but we don't expect it to shatter. Okay? So there are predictable ways things break. That's all we're doing in mass spec. Those predictable patterns, we can evaluate the pieces, and then what do we do with those pieces? We reassemble it to figure out what was the parent structure that made it. Okay? So there is a lot of information that can come out of this. So here's our ethane. We're breaking that carbon-hydrogen bond, which causes that to ionize, or we could have broken there, or we could have ejected an electron directly from the carbon itself. Right? So there's a lot of different ways that we could break this thing apart. And again, it drives off of cation stability. So one of the things that would be useful is if you could predict cation stability. I would bet you can. So take a look at these three cations. Are they the same? That's 4 for the record.
I was like, yes.
They are all the same. There's no difference. Okay, the bottom one is different from what? From the top one. So the top 3 are all the same. Okay, they're all different. We have all different carbocations. Do I expect them to all have the same energy? No? Okay. Which one is the most stable? Okay, I heard the last one because it has no hydrogens. The first one because it has hydrogens. Hedge bets. The number of hydrogens is not directly relevant. What makes all of these unstable? They're charged. You can do better than that. What about their positive charge? They're missing an octet. So what would make them more stable? Fulfilling the octet. Well, they're all cations. We can't fulfill the octet. What would make them more stable? To satisfy that octet, what would we need to bring in? Electrons. So to make these more stable, what do I need? You actually already said it. Polar, bringing in a secondary piece is going to make all of them equally stable, so a secondary piece can't work. We have to find internal. Okay? Before you get help with the class, you always struggle on your own. Then you get help. What do we need to stabilize a positive charge? Negative. What things are negative? Electrons. So what do we need to stabilize a positive charge? Electrons. Cool. Where do we have electrons? In the core. So the core of each of those carbons is different. No. Okay, so the core was awesome. We have electrons there, but it's not different. Try again. Where else do we have electrons? In the bonds. So they all have different bonds. No, they all have 3 bonds. Each of those bonds with 2 electrons in them, which means still not different. Keep trying. The atoms surrounding those bonds are different? How so? The number of carbons. That's the same as saying the number of hydrogens. That's not our answer. Remember, our answer was we need more electrons. The number of electrons available, I like where you're going with that. We need a little bit more nuance. Carbon has more electrons. Really? That's why it's 6 versus 1. Yes, carbon has more electrons. What did I need to stabilize the cation? More electrons. Which of these is the most stable? The bottom one, because there are literally more electrons around it. It might be nice to name this structure, right? I come up with a nice universal name. Calling it 3 carbons is a little weird, right? You may have heard reference to tertiary. What is tertiary in reference to? 3 carbons connected. You might have heard secondary. 2 carbons connected. You might have heard primary. 1 carbon connected. You never heard of zeroary, but you should. The other one is methyl. There are no carbons connected. That methyl or the zeroary carbocation is the least stable because it has the least amount of electrons around it. The tertiary is the most stable because it has the most electrons around it. Whenever we form a cation, at least in mass spec, we also form a radical. Turns out radicals have the same activity as cations. They're missing an electron. Okay, so a tertiary radical is more stable than a secondary, more stable than a primary, more stable than a zeroary. Okay, that's kind of cool. That's a big piece that mass spec gives us. That cation reactivity we will use when we talk about reactions in substitution. That radical stability we'll talk about when we talk about radical reactions. Mass spec gets us started on that path. You think you got it? You're like, no? Too bad. I think you do. Which one of our anions is most stable?
The one with the top electron.
What makes it most unstable? It has more electrons. So what do we need to stabilize it? Less electrons. Which one's the most stable anion? The top one. You do have it. That was awesome. We were like, you're full of crap. That's fine. You're at least right? Okay, so mass spec. This is what I get out of mass spec. Okay, the M+, the peak furthest to the right is your molecular weight. Okay, you can do an unsatulation. That word will get you your double bonds or rings. Okay, there's a formula to do it. I don't have that formula memorized. You are welcome to look up that formula. I'm sure the textbook gives it to you. Okay, I just don't see that worth my effort unless I'm forced to ask that question. Okay? After that, if the M+ is odd, I know I have an odd number of nitrogens. If I have an M+2, some people have been having a hard time with this. Okay, I understand the nomenclature is a little bit weird and it gets a little bit wonky. M+ versus M+2. What does it mean to be +2?
2 more.
Add 2 more. Add 2 more to what? The M+. Okay, that's it. So if you get an M+ at 97, what should you be looking for? 99. So you have an M+ at 97. There's another peak at 99. Okay, that would be an M+2. If that M+2 is there, that could mean you have more information. Okay, the could means you have to evaluate its height in comparison to the M+. If they're about the same height, you know bromine's present. Okay? If you know it's, and this is technically backwards, a 3-to-1 height, then you know chlorine is present. Okay? You would have to see spectra that show these so that you get familiar with these patterns. Okay? Last one, iodine is massive. So if you have a massive mass, you probably have iodine. And it has to be really freaking massive because it's not just 130. You have to account for all the other atoms, right? So the smallest thing that you could get with iodine would be what? What class is this? Yes. Why are you adding 12? This is an organic chemistry class. You have to add at least 1 carbon. But then carbon would need how many bonds? It needs its 3 hydrogens. Whatever that mass comes out to be would be the smallest possible mass with an iodine. Okay? For the sake of this class. The odds that iodine shows up at all is just limited. Okay? It's not worth the effort. Okay? So, can you get more from mass spec? Absolutely. Okay? Like I said, a forensic scientist or bomb specialists know how to study the explosion patterns and pieces that come out of a bomb to be able to reassemble it, to get enough information to say this is where the bomb was located and this is who made it. Right? That's after an explosion. Right? The exact same thing can happen in mass spec. But you have to have those skills and study habits to figure out how to break that apart. That requires looking at each of the individual pieces that came out of this. Every one of those peaks is a piece. You would have to study all of those pieces. Okay? It is insanely powerful. It is used very often, okay, in industry because it is that useful. Okay? That said, it's not used in academia quite as much, and I don't know why. Okay? It's still used, it's just not used as much. It might be cost. Okay? So if we were to go through and look at this, what we're looking for are multiples of 12. Why multiples of 12? We're looking at carbon structures. So if we started with an 86 and I dropped to 71, what did I lose to go from 86 to 71? A mass of 15. What would be a mass of 15? A carbon and 3 hydrogens. So I'm ejecting a methyl. Okay? If I lose that methyl, I would have that remaining piece, which would mean that would be a carbocation, yeah? Secondary carbocation. Okay, that's not too bad. That could exist. Okay? So what we're looking at is how do those pieces fragment and fall apart? That requires a lot more effort that I won't ask you to do. You are welcome to do it on your own time. Okay? You were already broken anyway, so let's just keep going. NMR, okay, it's like 2 minutes. Won't get much. NMR is talking about magnets. Okay, it turns out atoms are magnets. Okay, and in particular, nuclei are magnets. Certain nuclei. They have to have proper spin states for their nuclei to express a magnetic field. Okay? But let's just say, hey, they are magnets. If I now drop them into another magnet, is that going to change, or am I going to see an interaction between those? If I take one magnet and I bring it near another magnet, do I see a change in interaction? Yes. They could attract. They could repel. But ultimately, they are going to align with each other. Okay? That alignment, we have built instruments to detect. Okay? That's what NMR is. All we're looking at is how a magnet interacts with another magnet. Right? And we can detect that pattern. Okay? There are different spin states associated with our atoms. They're referenced typically as alpha and beta. So if a nucleus is magnetic, it will have a spin state, either alpha or beta. Okay? In my analogies, I usually reference them as up or down. Okay? So if we're looking at a standard sample, it's constantly just kind of fluctuating all over the place. I will now put it into a large magnet. That's now going to cause it to align with the larger magnet. Okay? Now the fun part. Once it aligns, we don't see anything. We have to see it change to get to the major alignment. That's where what we're going to fire at it are radio frequencies. Why radio frequencies? Guess what radio frequencies do? They mess with magnets. So the radio frequencies will cause the sample itself to change its spin. What we now do is can time how long it takes to realign to the external magnetic field. The time it takes, we can correlate to the environment that that secondary magnet is in. Okay? That's what NMR is trying to do. And that is crazy. But that's its attempt. Not all nuclei are magnetic. Conveniently, hydrogen, simple hydrogen, is magnetic. And because hydrogen makes up 99% of all hydrogen, protium makes up all 99% of all hydrogen, we can detect hydrogen in magnets very well. Right? And that's why we look at HNMR. Turns out carbon also has a magnetic moment, but it has to be carbon-13. What becomes the problem with carbon-13?
1%.
It makes up 1% of all carbon, which means it takes a whole hell of a lot longer to get any information out because we're now only probing a very small fraction of the atoms in our sample. Okay? With that, we'll go ahead and stop.